Moving on here to friction, which is our next specific force that we're going to talk about. So friction is a resistive force, as you guys know, and really it's caused by interactions on the molecular level. So ultimately, when two objects are sliding or in contact with each other, the atoms and molecules in the one object interact with the atoms and molecules in the other. And that's what ultimately leads to that force of friction, is those interactions on that microscopic scale. Frictional forces depend on two things. The first is the two surfaces involved that are sliding across each other. And that really is just how smooth one thing slides across another. We know that certain surfaces slide more easily across things than others. For example, silk a lot of times slides easily over the top of a surface, whereas sandpaper doesn't slide nearly as easily. It's a lot rougher. Okay. We see this with driving. A dry road and our rubber tires, there's a lot of friction. There's a high coefficient of friction between those two surfaces. However, when it's icy out, that coefficient drops significantly and the roads become very, very slippery and dangerous. Okay, so the first thing that affects the amount of frictional force that we have is what two surfaces are interacting. And the second thing that affects it is the normal force. All right, how much those surfaces are pushing on each other. So there's a really easy experiment you can do right now, and that is rub your hands together, right? That creates friction. That's kind of like the elementary school friction, where you feel the heat being generated and they talk about how that's friction, but that is friction between your two hands. Now, push your hands really hard together and try rubbing again, and you're going to feel a lot more friction now, okay? And the reason is we now have a greater normal force between the surfaces of your two hands, and that increases the force of friction. We're going to use a symbol for, we already know what normal force is. Normal force is just Fn. For coefficient of friction, we're going to use this symbol, the Greek letter mu, M-U, okay? And mu, that coefficient of friction, happens to be our first number that is allowed to be naked, all right? Mu is a unitless quantity. It doesn't have units, so even if we wanted to put units on it, they don't exist to put them on it. But it's going to be our first unitless quantity. We accept the fact that it's a naked number, and we just move on. All right. One last really important point, and we'll talk about the other case in a second, but for sliding objects, any object that's sliding across a surface, friction always opposes the direction that the object is sliding, opposes the velocity of the object. Okay, that's an important thing to keep in mind, and we'll talk in a few days about the not sliding case. So the equation, the specific way that we find the force of friction is with this equation, that the force of friction is equal to mu k. That's that coefficient of friction that we were just talking about, how smooth one object is as it slides over the other, times our normal force, Fn. Okay. The k next to the mu, I'll tell you briefly, stands for kinetic, and that just means moving, which in this case means sliding friction. So this is the formula for finding sliding friction. We will talk about the non-sliding case in a little bit because it does get more complicated, but that's what the K stands for. So here we have our friction equation, Ff equals mu K, the kinetic coefficient of friction, times our normal force. So this is going to be another force that we can now calculate. All right, when doing these problems involving friction, there are a few important things to note. Obviously, we're always doing the important things like drawing a picture, writing our max and may, all those good things every single time. Some other things specific to friction. The first is this. Friction depends on the normal force. Okay? Typically, the normal force is a y force, and the force of friction is an x force. So we will have to make what I call the big move, and what that is we solve for the normal force, and then we're going to bring it into our equation for friction to solve for friction. Okay? So that's one kind of goal that you want to have in the back of your mind when you're doing these problems. The other thing, and I literally cannot stress this enough, all right, do not assume that the normal force equals the force of gravity. This is something that will happen often. Oftentimes, normal and gravity will be equal, but it's not always the case. And there's nothing that says the normal has to equal the force of gravity. Once we have another vertical force, or we have a situation where the floor itself is accelerating. I know that sounds ridiculous, but you may or may not get a problem with an object sliding across the floor in an elevator that's accelerating up. So once the floor itself is accelerating, this idea is out. So even though it might very, very frequently be equal to the force of gravity, we can't just jump to the conclusion that the normal force equals the force of gravity. Let's go ahead and try a practice problem here. We have a 25 kilogram box is being pulled across the floor with 100 newtons of force at an angle of 20 degrees above the horizontal. Coefficient of friction between the box and the floor is 0.31, and we want to know the acceleration. So I'm going to start by identifying all the forces I know. I have this pulling force going up at an angle of 20 degrees. I have my normal force because I'm sitting on a surface. I have the force of gravity because we're assuming this problem takes place on Earth and gravity is always going to be there. And then we have the force of friction. We know that one must exist because we're given a coefficient of friction and it's sliding across the surface. So unless it is specified that it's frictionless, we can assume that there is friction when an object is sliding across the surface. Now, first thing we're going to do, and this should be jumping out at you right away, is to take that angled force and break it into its x component, which is Fp cosine 20, and its y component, which is Fp sine of 20. Once we have that, we're thinking about max and may. It doesn't really matter which one you start with. I'm just going to start here with my y forces. Sum of the forces in the y equals may. So what do I have vertically? I have my normal force plus Fp sine of 20, okay, minus the force of gravity equals m times ay. I'm also down here going to set up my x equation. Sum of the forces in the x equals max. So what do we have horizontally? We have this Fp cosine of 20 minus that force of friction, and that is equal to max. Folks, if you can get to this point with your two equations filled in with the specific forces in the x and y direction, you are in great shape. That needs to become something that happens automatically every single time. Now that I do have that, I can start filling in for the things that I know. So for one, I know my acceleration vertically is 0. Okay? As an object is being pulled across a floor, that means it's not accelerating up and down at all. So I can say that my y acceleration, my vertical, is 0. And then I can say Fn plus 100 sine of 20 minus mg, subbing in for that force of gravity, is equal to 0. I end up then getting Fn plus 34.2 minus mg, so 25 times 9.8, or 245, equals 0. And then I end up getting a normal force of 210.8 newtons. I'm now going to go ahead and start setting up my y. So I know in the y direction that Fp is 100, so Fp cosine of 20 minus the force of friction, which we just found out was mu times our normal force. And that's going to be equal to my mass here, which is 25 times my x acceleration. And that ultimately is what we're looking for. What is the acceleration? Well, there is none vertically, so we're simply looking for the horizontal acceleration. So I can get a numerical value here for this 100 cosine of 20, and that's going to be 93.97 newtons, minus, I know my coefficient of friction is 0.31, times, oh, look at that, I needed that normal force here. This is what I like to call the big move. We take that normal force from the y, move it over to the x, and that's equal to 25ax. And so I end up getting 28.6 equals 25ax, so my x acceleration is going to be 1.14 meters per second squared. Moving on, we have a car that is initially traveling at a speed of 12 meters per second, skids to a stop over a distance of 8.5 meters. We want to know what is the coefficient of friction between the tire and the road. First thing we would do, of course, is draw that free body diagram. So I have my normal force going up from the road because it's surface. force of gravity going down, and I'm going to say that my car is initially traveling to the right, and that means that my force of friction is going to be going back to the left, in the opposite direction of our motion when we're skidding to a stop. That's the case with kinetic friction. Once I have that, I'm going to set up my F equals ma, of course. I don't have any forces at angles here, so that saves me a little bit of work. But in the y direction, I have some of the forces. The y is may. My y acceleration is 0 once again. I'm not accelerating up and down as I skid to a stop. My forces then, I'm going to have Fn minus Fg. Those are the forces I have in the y direction. And they're going to be equal to 0. So I can say that Fn is equal to Fg, which is simply mg. I don't have a ton of information here, so I'm just going to leave that as is for now. I've gone as far as I can right now. In the x direction, some of the forces in the x is equal to m times my x acceleration. The only force I have is the force of friction, and I'm going to say it's negative because I'm using that standard convention where right is positive. Although, as I've said many times, as long as you're consistent, you are good. So that's going to be equal to my mass, m, times my x acceleration. So negative mu times my normal force is equal to m times my x acceleration. Now, you might have noticed something here with this problem, and that is you're given some information about the motion of the car. You're given a velocity, you're given a distance. These are kinematics things. So the other thing we can do here is we can set up our kinematics. And what that's going to allow us to do is it's going to allow us to solve for the acceleration. That's how we can link the motion of the object to those forces. And if we find that acceleration, it's going to take us one step closer to finding the coefficient of friction. So I have my distance there of 8.5, starting at a speed of 12 meters per second and skidding to a stop, so my final is 0. And I'm looking for that acceleration. I'm going to use my VF squared equation, so I can say 0 squared equals 12 squared plus 2 times A times 8.5. What we really end up getting there is negative 144, bringing that 12 squared over here, is equal to, and I'm going to multiply the 2 and the 8.5, so 17A. And I end up getting that my acceleration is negative 8.47 meters per second squared. Now that I have that, I can go back to my max, and I'm going to take everything that I found and sub it in. So I don't know mu, that's what I'm looking for. I don't know Fn, but I do know that it's equal to mg. I found that over here with my May equation. I also just found that my acceleration is negative 8.47. So I can divide out the m's, and what I'm left with, and I can make both sides positive, what I'm left with is mu times g, which is 9.8, is equal to 0.847. And so I now have a mu value of 0.86. And that's my coefficient of friction. Moving on to our last kinetic friction problem that we're going to do together. And in this one, we've taken those numbers and we've gotten rid of them. You knew this was coming sooner or later at this point in the year. And we have a slightly unique situation too, because now we're pushing a box up a wall, literally. Okay? And that's going to change some of the forces. So let's think for a second about what forces are acting on this box, which has a mass of m. So we have a normal force, and that's actually pushing out on the box because the box is, or the wall is our surface. We have the force of gravity acting down, of course, because that's always there. We have this pushing force, Fp, at some angle, and that angle is measured from the vertical here, and so it's going to be measured from the vertical here as well. And lastly, we have a force of friction. We're told that there's a coefficient of kinetic friction between the box and the wall. So that means there's going to be a force of friction going opposite the motion of the object. We're told that the object, the box in this case, is being pushed up the wall. Therefore, friction opposing the motion would be going down. First thing, I'm going to take that pushing force, Fp, and down here I'm going to break it into its components. Theta is that angle we knew, so the y side is FP cosine theta, because it's the adjacent side, and the x side is FP sine of theta. Once I have that, I can start setting up my maxima ma, so sum of the forces in the x equals max, and in the y, sum of the forces in the y equals may. This situation is a little bit unique because we have a normal force in the horizontal direction. That's going to change things. But I'm going to set, the basic setup is not going to change. The basic idea behind this is not going to change. So in the x direction, I'm going to look at my forces. I have Fn minus Fp sine of theta. And that actually is going to be equal to 0, and here's why. This box, as it moves up and down the wall, is not accelerating left or right at all. So that x acceleration goes to 0, and that means that my normal force is simply equal to my pushing force times sine of theta. Moving on to my y, what forces do I have acting in the y? Well, we have Fp cosine of theta. That's our one vertical force right here. We have the force of gravity going down, and in this case we also have friction also going down. And that's going to be equal to the mass times the y acceleration of the object. Now, we do have another quick break here, and that is that the object is being pushed up at a constant speed, which means my acceleration is 0 for both the x and the y. Okay, so I can say that Fp cosine of theta minus, and I'm going to sub in for gravity, mg, minus, and I'm going to sub in for friction, mu Fn, must be equal to 0. I'm going to go ahead here and do the same thing that I always do, and that is taking this Fn and subbing in here. I know it seems like a lot of algebra, but let's stick with our basic idea of solving these and see what happens. So we have Fp cosine theta, no substitutions there, minus mg minus mu times Fp sine of theta equals 0. I'm going to move that mg out of here and move it to the other side. And I'm going to take an Fp out of these two terms that remain. I'm going to factor out an Fp. So we're going to have Fp times cosine of theta, the mg already moved to the other side, minus mu sine of theta. So if we go ahead and solve for our pulling force, we get that it's equal to mg over cosine theta minus mu sine of theta.